summarize a little bit what we have done last time, and then I will redo the harmonic oscillator because it was a little bit fast at the end, and because I would like, since this is something that most of you haven't seen, to tell you a few fun things about that other way of solving it. But let's summarize a couple of things that we have seen last time. So when we are at fixed temperature, we compute the partition function, which we do by summing over the energies of all our states, e to the minus beta times the energy of the state. And you have done in the tutorial a few examples where the energies are very simple. Like if there are two energies, you have two terms in the sum. If you have many spaced by n, it's just a geometric sum. So often we can compute this analytically. Often we don't care about, we cannot compute it analytically, or we can compute it for very large systems or big energies. Because then this summation is effectively continuous, because there are many states with a given energy. And it becomes effectively a continuum where I integrate over the energies how many states there are, the degeneracy, which fights against the energy. So very energetic states are suppressed, but states that have lots of degeneracy are enhanced. And because this entropy is huge, in practice we can use a saddle point approximation. We can compute this by saddle point. And it's a fake integral, because in practice only one energy contributes, and that energy is given as a function of the temperature by the saddle point equation. So saying that we are integrating over all energies, it's true, but it's also true that in practice, if you tell me that you are at some temperature, you are at some effective energy, and fluctuations of that energy are suppressed in the thermodynamic limit. And therefore saying that we work at some fixed energy or we work at some fixed temperature, it's basically the same thing. Okay? Is it clear? Yeah.
Just one question though. So when taking the partition function, you take an integral over energy, which has units energy.
Which has, sorry?
The units like energy. I'm trying to make a unit calculation, like trying to make sure that the units hold. But I'm having trouble. Is the energy unitless here?
Okay, so because there is you mean that I'm setting Boltzmann constant to 1, right?
Oh, okay. So regarding that.
So I'm measuring everything in units where Boltzmann constant is 1, right?
In the equality where we use the saddle point approximation, on one side we have units of energy, on the other it seems to be unitless. So even Boltzmann's constant wouldn't fix that.
Or for example, we are saying SE is equal to n times logarithmic energy, but energy has units, and I'm having trouble.
Yeah. So I'm not sure what the constraint is. Of course, if I introduce Boltzmann constant, multiplying logarithms of the number of states, all the units are okay.
Energy measure.
You're just worried with this thing here, that this is a sum of numbers, and here I'm integrating over energies.
Exactly.
Okay. Yeah, that's true. That's, for example...
Energy of states also has 1 over energy.
Yeah, that's right. So if you remember this energy of states, for example, when I took the derivative, so there could be some simple measure factors to fix. For example, do you remember this energy of states was an area, was like number of degrees of freedom minus 1. So that minus 1, you can think that there is over E here. And that makes this dimensionless. But even if there's some small prefactor here, it doesn't matter, because what matters is the exponent. So yeah, so sure that in going from here to here, if I want to integrate over energies, I can divide by some energy spacing, say, to make it dimensional. Yeah. But then it's just a number, and it doesn't matter because that's just normalization of the partition function, right? And then when I compute averages, I divide. I sum with some quantity here, and I divide by the partition function, so all those things would cancel out, right? But it's true that to make it dimensionful, we can say that if my level spacing has some level spacing, typical level spacing epsilon, I can say I put here some 1 over epsilon as a normalization just to get the dimensions right. Any other question? Okay, and then as we saw that the fluctuations, actually I'm writing here in colors a couple of things that I'm going into a little bit more details in this summary than last time. I did not say last time, but it's true that this quantity that we computed, the expectation value of energy square minus the expectation of the energy square, one way of saying why am I calling this a fluctuation? It's because it's exactly a fluctuation. It's the average of the energy minus the average value of the energy, right? So written in this way, it's obviously a fluctuation, right? If the energy is equal to the average, then this quantity is 0. If this average is very different from 0, it means things are fluctuating a lot. And the fact that this is equal to this, you see it's obvious, right? You can see it by head, right? When you square this, one term is this guy, and all other terms give this guy, and there are +2, -1, -2, +1, and it gives this. Okay, so if this is not obvious, it could be one of today's exercise to check, to understand why this is true. And therefore, fluctuations are very small. So again, if you give me some temperature, I compute what the average energy is. Now that I know what the average energy is, I could have said I work at that fixed average energy. And that's equivalent. Okay? So, of course, these fluctuations are super tiny, but super tiny means really, really tiny for a real system with a gas here in the room, for example. Fluctuations are super, super tiny. But of course, we should keep in mind, because tomorrow we are going to put things in a computer, that if the lattice is like 30 by 30, square root of 30 by 30 is 30. Oh, it's a few percent. 1 over 30, it's like 10. It could be easily 10% error, right? Okay, or a few percent error. Oh, that's life. Okay, if you could make 300 by 300, it would be like 1% or 0.5%. It would be better, but that's hard to simulate. Okay, so that's how it. Now, one example we did was a gas. We computed how many states there are by integrating over phase space. So the positions give a trivial volume to the number of particles. And then the momenta, we said that the sum of momenta is equal to the energy. So sum of momenta square is a sphere, which has this radius, right? Because we have sum of p square equal to the energy times 2m, right? When I multiply over by 2m. So it's a sphere of that. And then, as we said, we have a sphere. The area is how much the sphere increases. When I increase the energy a little bit, that's how many states there will be there. So we take the derivative of this volume. This volume, what matters is energy to this big power. But here I'm writing all the factors, if you are curious. And then we said, okay, there are this many states. So the probability of finding particle with this momenta is this ratio here, where I say that because I'm fixing one particle, now I have n minus 1 particles. And because I fix one particle, instead of energy E, I have to subtract this energy and to distribute the rest. And then I divide this by the total thing with total n, total energy. The ratio that matters is this, effective energy over energy to the power of this. And this is the definition of exponential. So it gives me the Boltzmann weight, e to the minus beta, p squared over 2m, where beta is this. So it's kind of a simple example where we see this Boltzmann weight appearing. Okay, so since the harmonic oscillator thing was kind of new for everyone, let me recap how it worked, because maybe it was a little bit too fast, and make a few comments that I think are interesting. So we said that we define P of x to be, its definition, h bar over I, derivative with respect to x of the logarithm of a wave function in a one-dimensional quantum mechanics. And this object, therefore, as for the nth excited state, my wave function psi n as function of x will have 1, 2, 3, n zeros. Okay. So P behaves close to each of these positions, xj, behaves as h bar over I, 1 over x minus xj. So this thing is the residue, and it's fixed, because close to each 0, the wave function is a times x minus xi, and the derivative couldn't care less about a, right? It just gives 1 over x minus xi. Okay, good. So this is what P is close to just based on the definition. And on the other hand, Schrödinger equation said that p squared minus 2m, I'm going to write, I forgot if it's e minus v or v, yeah, it's e minus v. E minus v is equal to I h bar over 2m p prime of x. I just reshuffled a little bit the terms that we wrote yesterday. Okay. Actually, for what I'm going to do now, this was not a smart idea, so let's not do it. Minus equals 0. Is this what I wrote last time? Can you check please in the notes? Because last time we were careful with signs. So is it like this? So I just multiply everything by 2m. Yeah? It's okay? Good. So now, then what we said was that this potential here, so far it's true for any quantum mechanical system, but this potential is 1/2 m omega square, right? So we see that P should behave like I m omega x at large x, okay? Right? And before we so that's because when I square I get minus is plus, so then that's the way, sorry, I forgot x squared, right? So that's the way that this equation at leading order in x squared works, right? And before going on, let's notice that with this thing, I can ask, okay, so if P behaves like this at large x, what does it mean for psi at large x, right? So P going like I m omega x means I multiply by I and it becomes minus x. I integrate and it becomes minus x squared. And I exponentiate, so psi is e to the minus x squared. Okay? So this is saying that psi is a Gaussian at very large x, which is what we know from the solution of the harmonic oscillator. If you remember, it's a Gaussian times some Hermite polynomials, right? So that's fine. So at large x, it does decay exponentially. Okay? So it's good. Okay, so P is I m omega x. And then we said that, well, on the other hand, it should have those poles. So let's try to write a function which has those poles. Sum over n, 1 over x minus xj. And now we were saying, that this is at large x, that this is a good guess for P, because now you see that this behaves as I m omega x plus, each of these terms is roughly 1 over x, so plus h bar over I, there are n terms over x, plus order 1 over x squared, that we could compute, no problem, it's just expanding this term here. And in particular, we see that this is a nice thing, that there is no constant term, which is good, because if there were a constant term, this would not work. Because if there were a constant term, when I square P, I get a term linear in x, and there is no term linear in x in this equation. So that's good, since there is no term linear in x at large x in the equation. Okay? And therefore, we have a function with the right asymptotic, the right poles, and therefore this should be this should be our function. And then when we plug this term into this equation, well, the leading term cancels. So the term when I compute p squared cancels because it was designed to cancel. So let's check the subleading term. And the subleading term, the cross term gave 2m omega h bar. So this we are plugging into the equation at large x and looking at the constant term. So the square of p gives this times n, right? Another constant term is from the energy, minus 2m times the energy, and another from the derivative. The derivative acts there, and there is and I, so plus I, let's see, 2m. Was this correct? Did I forget to remove this?
Yeah, by 2m, there's no factor.
There's no factor, right? So just like this. So plus m omega h bar. So when we compare, we learn. So there are then plus order 1 over x that we don't care. We are looking at the leading term now. So we get that the energy is h bar omega n plus 1/2. Right? So let me recall. So this is from p prime, and this here is from p squared. Okay. So any question here? So I think this is the fastest way of getting this. But now let's see what else we could say about this problem. Well, one thing we could do is now say, well, but what about the value of these xj's? What are these xj's? Okay. So how do I try to find the xj's? I can say here is an equation, right? This equation must be true. And it must be true for all x. So in particular, I could zoom in close to x equal to xj and impose that this equation holds. Right? So when doing so, it's easy to see that the term, when x goes to xj, I take a derivative. So it looks like there is a double pole. But I also square. So there's also a double pole, because there is also the term 1 over x minus xj. And it's very easy to see that the double pole cancels. But there is a single pole that survives, and we should impose that the residue is 0. So if you impose that the residue at x equal to xj of the equation is equal to 0, well, the energy and the potential, they have no poles. So all that we care is about this p prime and this p square. Right? And if you do it, you get the following. You get an equation of the form xj equal, I'll write the equation, then we can check if you want. So let me write it. So xj equal xj times the constant a. Let me work out this constant a in a minute. Plus summation over k not equal to j of 1 of xk minus xj equal to 0. So give me 1 second. So let me put a minus here. And let me say that when this guy is bigger than this guy, this is plus. Yeah, this should be okay. Where this a is, okay, so let's see, let's compute this. So the residue, let's see, so p prime has a double pole only, so it doesn't contribute, that's good. So it's actually just from p square. So we are imposing that p square. Right. We are imposing that p square basically has no residue when x is equal to xj. And there are two terms that contribute to the residue. When I square this guy, I have the cross terms. When I have x minus xj times x minus xk, and that's where the sum comes from. And when I multiply both, I evaluate x equal to xi, so I read off a term linear in x. Okay? And then if you work out carefully the prefactors, what should they be? So this one has nothing, and this one has m omega. So the relative coefficient is some m omega over, but this was h bar square, right? So one of them, the sum would come with h bar square, and the square would come with m omega h bar. So the ratio is m omega over h bar. So this A should be m omega over h bar, and probably there is, yeah, it's probably just that.
Why are we doing this?
Okay.
Sorry.
Yeah.
Why do you require the residue of the equation to be 0?
So this equation must be 0 for all x, right? For any x.
Right, yeah.
So in particular, it cannot be a function with poles, right? This is, so this defined like this. If I plug this expression here, it looks like it's a function of x, right? So that function is 0 because the equation is 0. So we already showed that that function, the leading term, when I plug it, cancels. And that fixed me my energy. Now I'm checking that the full equation cancels by zooming in close to another point where things simplify. Now, it is true actually that now if you can just check that the equation is trivial, it will be satisfied. If this equation is true, then this equation is satisfied everywhere for any x, right? But because we already checked the asymptotics, and this equation only has single poles, if you check that now you don't have single poles and you already checked the asymptotics, you are done, right? Again, let me repeat this argument slower. We said that we have a function that goes linearly with x, right, for p. This function here, this thing here, this left-hand side, we canceled the leading and subleading terms at large x. So now this is a function that at most decays at large x, right? Because we fixed the energy. So now this left-hand side decays at large x, right? Because we already canceled the growing term and the constant term. So now it decays. Now we have a function that decays and which has a few poles, right? If I show that the poles are not there, the function must be the function 0, right? There is no function that decays and doesn't have poles inside, right? So if you have a function, it's a rational function clearly, it decays, and it has no poles, well, then it's 0, right? There's no rational. So because we already showed that it decays, checking that this is true for all x is the same as checking that it has no singularity. And checking that it has no singularities is simpler because you just zoom in close to the singularity. And as you see, for example, this doesn't contribute, and only this contributes. So it's simpler for the analysis, and it's easy to see that you get this equation. Okay?
So saying this, the residue would be just like evaluating this equation at a pole.
Yeah, the residue is saying that the equation close to this pole is saying that this equation right now, the left-hand side behaves like 1 over x minus xj times something, and that something is this, that must be 0. Because the function should not have singularities there. The function should be the function 0. Right? Was this too fast? You can do it a bit slower if you want. Okay? Anyway, so let's do it a bit slower. Let's do it in another way. This is a bit of a detour, but I think this is kind of nice things to understand how it works. Okay? So, first, let me emphasize that there is no double pole. And there's no double pole, even though naively it looks like there is, because p prime contains 1 over x minus xj square. So it looks like it would diverge quadratically close to xi, right? The derivative with respect to x is x minus xj square. But p square is exactly that as well, right? Contains exactly that term. So that term will cancel. Right? So there is no double pole. Is it clear for everyone? But there could be a single pole a priori, not from p prime, but from p square. Because from p square, when I square this sum, I get cross terms. So definitely there is a single pole. And I get this times this, there is also a single pole. Okay, so there could be single poles. And indeed, the way to cancel these single poles is to impose that this equation is true for any j, which goes from 1 to the number of particles n. Okay. Now, if you impose this equation, now you are good. You have no single poles, you have a function that decays at infinity. It has no single pole, so it is 0. So the equation is satisfied. Do you agree? Now, it might look a little bit like I'm using some fancy arguments, so if you want, I can do it more explicitly. So let's do it more explicitly because it's very easy. So let's just plug our definition of P into the equation and check that it solves the equation, right? This is a fancy argument, but plugging is the simplest thing. So let's plug it and see how it works. I am omega x minus h bar over I, sum of x minus xj, sum over j. I want to square this term. Let me write the p prime right away. Minus I h bar. P prime. P prime is what? Sorry, why did I put a minus? No minus. Plus. P prime is minus h bar over I, sum over j, 1 over x minus xj square. Do you agree? Plus 2m e minus v. I want to show that this is 0, so let's try to see it.
Are you missing the term in p prime from the linear part?
Yeah, I am. The term p prime from the linear part is just I am omega. Right? Okay. And now what we see is the following. So let's see how this works. So we get the square of this term. It cancels with the potential, so I'm not going to write it. Then we get the cross term, which is 2 h bar m omega x sum over j 1 over x minus xj. Right? And then we get the square of this term, which is minus h by square sum over j and k 1 over x minus xj 1 over x minus xk. That's the first term, right? It's two sums that I just wrote like this. And this here, I can say that it's equal to the sum over j equal to k plus sum over j not equal to k. And when it's equal, when this is equal, it cancels this term here. Right? So when it's equal, this term when it's equal just cancels this term here. Right? And therefore, I can stay with this. And now it's obvious that I have only single poles because the double poles just canceled. We just saw it now explicitly, right? And now we only have single poles. Now we use something a nice identity, and that's the only reason why I'm doing this exercise here. It's because I think this is an identity everyone should know, which is that this is equal to 1 over. So let's see, what is this function? It has a residue when x is equal to xj. So let me write 1 over x minus xj. And what's the residue? Is xj minus xk. So 1 over xj minus xk. And it also has a residue when x is equal to xk. So plus 1 over x minus xk, where the residue is xk minus xj. So 1 over xk minus xj. Okay? But this is just symmetric. I sum over the difference. So I can just keep this one and multiply by 2. And therefore, this, which I'm doing, I'm just doing this term now here. Right? So this term, I'm simplifying it. So that term there becomes 2 h bar m omega x summation 1 over x minus xj plus summation over j h bar square 1 over x minus xj, and then summation over k, which is not equal to j, 1 over xj minus xk. And there, as I said, there are two terms, so factor of right? And both as this and just replacing the labels is the same thing. And now you see that concerning the deriving the equation I said, it's done, right? So the residue, we will continue the exercise, but you see the residue of x equal to xj comes just from these two terms. And one term gives this when I plug here xj, and the other gives this times this, which is just the sum that I have there, right? So we just check that the residue, canceling the residue, gives this equation here, and hopefully this factor is right. You can check now. Right? So the 2 cancels the 2, so it was okay. There is an m omega divided by h bar, so it looks like it's okay. And here I wrote xk minus xj, so the sign would be plus, but there I think I wrote xk minus xj, so the sign is minus, so everything is okay. Right? Good? So from here we see that the residue is good, so we can write this, let's see. Right, so we can see, let me think what's the best way to do it. Okay, let's like it. What I'm writing is not this term, right? It's this term minus the diagonal, because the diagonal cancels with the term here, right? Of course, I'm being a bit schematic. So let's even write it more explicitly. This is the sum over j, 1 over x minus xj, times the first term is just 2 h bar m omega x, and the second term is plus sum over k not equal to j, 1 over xj minus xk. And what I can do here is replace this x by x minus xj plus xj. Do you agree? Now the xj term survives there, and the x minus xj cancels, so it just counts how many terms there are, right? So this becomes equal. So the x minus xj cancels this term, and it gives me therefore 2 h bar m omega n, just how many terms there are here, plus, and then I get the same thing that I have here with x replaced by xj. You agree? Okay, so now we are done. Now let's just collect the various terms. So let's just collect the various terms. So this, okay. So the square of this term, so there was also a term that I did not write, but let me write actually. Minus m square omega square x square plus, so this was the square of this term. Okay. So now let's see. So this term is cancelled with the potential. Okay. Then this term here, this constant, plus this constant, cancelled with the energy, and that is another way of seeing that the energy is what it should be, right? And finally, there was this term that cancelled with this term, and therefore everything cancelled. So the only thing we need to cancel is this here, with xj inside, and everything cancels. Right? So we just get this equation for j. Right? When I plug xj there. And then everything cancels completely, and the equation is just satisfied. But again, this was painful, and I did not need to do it because of what I said before. We had proven that this is obviously a rational function. We had shown that at large x, it vanishes. All we needed to do is zoom in close to a singularity. using all these identities, expanding things out, it was really a waste of time. Except that I think it's useful because you saw this identity that if you did not know, you should know because it's useful everywhere. Yeah. So that's the only. This is good. Yeah. Don't forget this identity. Nice identity. Okay. Okay. But now let's see what I wanted to tell you is that therefore we saw that let me summarize. So the summary is that the zeros of my wave function psi n, that is these values xj, obey this equation, which says that minus a constant, which apparently is m omega over x bar xj, plus the summation over k not equal to j of 1 over xk minus xj equal to 0. So it looks like we were trying to solve the harmonic oscillator and we got some equation for some position of the zeros of my wave function that looks itself like another statistical mechanical problem. And indeed, we can think of this x, so let's think of xj as some positions of particles. And then we think of this first term as some external force that acts on these particles. And let's think of this term as some interaction force between particle xk and xj. And we think of this equation as an electrostatic equilibrium condition. That is, we see that we have a particle, xj, which is in a constant force, that's proportional to the distance from the origin, right? So this force is the force that the particle feels with a potential which is a quadratic potential, which is nice because we are solving the quadratic oscillator, and we see that there is a force that pushes the particle back to the origin with a force proportional to the distance from the origin. So what we see is that we have a particle, xj, and there is a force proportional to the distance from the origin, 0, x, and this external force, F external, is just minus k times x, where k is this constant here. Right? So if there was no interaction, what would happen? We put a bunch of particles, they all go to the origin. They just have x equals 0. Right? But here, we see that particle xi and xj, they repel each other. Let's see that the signs work out. So there's a minus sign, so the force attracts the particle to the origin. When x is positive, it's negative. When x is negative, it's positive. So the force wants to push it back to the origin, right? It's a restoring force. What about this term here? When xk is bigger than xj, the force is positive. Let's see, so xj is, if xj is at the origin, xj is 0. And xk is, no, there is a wrong sign. Did I write the correct sign? Plus, minus.
J minus xk. Put it there.
There is a wrong sign somewhere. Painful. Xj, and here xj minus xk with a plus. So if I put k minus j, there would be a minus. Good. Sorry, 1 second. So x.
So you need a minus there.
You need a minus. K minus J. The J minus K is K.
No.
Here is j minus k.
Oh, that's idea. Yeah,
But he'll already change the sign.
It's changed.
That's alright then.
It's possible that you are right, but let me understand. So,
I mean, if these particles, if xj is farther back over than xk, yeah, but it's going away. Imagine this one with 0, and this one's positive. It's a positive, and it would be attracted because it would be pushed to the right side and it's not. Yeah, imagine xk is here and xj is here. It should be a positive.
Over here, you can see.
The sign when you have h bar square minus h bar square.
here.
Then to the next one, the next step.
And then here I put a plus.
Yeah, but
That's strange, right? It should be minus. And because it's minus, then here it's minus. And then there it's plus. And that's better. And now here I can flip xj minus xk, which I like more. Xj minus xk. Thank you. Good point. Okay, good. So then we see that this force wants to send particles back to the origin, but then this force, when xj is at the origin and xk is, say, slightly to the right, so xk is positive, there is a negative force, so particles repel each other, right? When this separation is positive, the force is positive. So which means that if I put a bunch of particles, they all would like to go to the origin, but they repel each other, so they cannot all go to the origin, and instead they form some distribution of zeros like this. So in the complex plane X, there would be some distribution of zeros that are the positions of these particles that repel each other and that are in this confining x squared potential. Okay. And in fact, we know what these solutions are. We know what the solutions to this electrostatic problem are. Can you guess? What are these xj? Okay, so I'll tell you. xj are just the zeros of their mid polynomial of degree n. Because that's the solution of Schrödinger equation. Right? And Schrödinger equation is a Gaussian times the Hermite polynomial. And you remember that each pole is just a position of the zero. So if you know Hermite polynomials and you plot them, here is an interpretation of the zeros of the Hermite polynomials. The zeros of the Hermite polynomials are describing the electrostatic equilibrium position of a bunch of particles in a confining potential. Okay. Now, I want to make one more comment, which is we have this Schrödinger equation, and there is a classical limit. And the classical limit is one where P is large. In other words, H bar goes to 0. But of course, this is dimensionful. So what it means is that it's much smaller, that H bar times P is much smaller than P squared. And therefore, in the classical limit, H bar goes to 0, which means quantities compared to H bar are very large. Right? So of course, I'm not sending meters to 0, right? I'm doing proper physics. So H bar going to 0 in the sense that if I see an H bar, I know I can drop it. So we can drop the minus I H bar P prime term. And therefore, in the classical limit, Schrödinger equation becomes P squared minus 2m e minus v equal to 0. In other words, let's put a classical index here. P classical is equal to square root of 2m e minus v. Right? Okay. So which means that if your potential is something like this, it can be quadratic, but it can be anything. It can be a cosh, for example. Then at some point it's equal to the energy E, and there is some segment here. Right? And now my P classical is a function which has a cut between these points called the turning points. So if I call this A and this B, then my P classical is a function that has a cut. The square root is 0 at A and at B, and there is a cut. And if I cross the cut, P goes to minus P, so I should think that P lives in a two-sheeted Riemann surface. And there is a cut that connects it. And under this cut, here I start with P, and when I go here, I have minus P. Right? Where P is just that function, square root of E minus V. So it means that when I go around a point, I come here, I need to go around twice to go back to the same point. That's the definition of a square root. Right?
What are these surfaces?
So I'm just saying that P, as a function of x, I should think that x lives on two copies of the complex plane. In what sense? In the sense that I start with x, and x is this function, right? But this function has a square root. So when I'm far away from the cut, it's all good. But when I go around the cut, I don't come back to the same thing. If my function is square root of x squared minus 5, if I go around the cut, I go to minus square root. So what does it mean? How do you draw that? You say that as I'm going around, I don't want to say that I just go around, because the function here is minus the function. So you say that there are two copies of the complex plane. And as I'm going around, I just come here. So this is just how you think of a function square root of x. If you think of a function, say square root of x, the way to think of it, you should not think that it's a function from the complex plane into the real numbers, into the complex numbers. You should think that it's a function from two copies of the complex plane, because when you are on one copy, you get plus square root. And then you go around and you get minus square root. And then you go around again and you get plus square root again. That's the definition of what's called a Riemann surface. But if you are not comfortable with Riemann surfaces, forget about the second sheet and take the first sheet. The first sheet is just a function which has a square root between these 2 points, which are the turning points of this potential, right? Forget about the picture, but this is clear, right? So there is a square root where the zeros of the square root are the turning points of the potential. Right? Good. So in the complex plane, I can draw in the complex plane, even if you don't draw the second sheet, you would agree with this picture, right? That in the complex plane, P is analytic, except that there are a branch point B where something happens, a branch point A where something happens. So don't draw if you want the second copy like I did there. But at least the first copy you would be happy with, right? Good. And now P is this expression here, and it has this cut here. However, the correct P has no cuts. The correct P is a function which is meromorphic and which has poles. Right? So what's going on here? Okay. So here we can ask cuts. What are these cuts? What are these square roots? P should have poles. Right? Well, we said that if we have a very excited state, it just has many poles. It doesn't have cuts. Right? So what is happening? So the solution to this small puzzle is that these poles are condensing into a cut. So what's happening is that you have many, many poles. But from far away, you zoom out and you see a continuum, and that's the cut. Okay? So it's like you have many, 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 many poles, but you are zooming out and you see a cut. In other words, more mathematically, we have a sum of 1 over x minus xj. This is like an integral over some density of poles over x minus y that goes from a to b. And this is what is going to become the square root of x squared, x minus a, x minus b. It will have this behavior. This is, I mean, I'm not saying that this is equal to this, but this function, now it's a continuous function that close to x equal xa is a square root singularity, close to x equal xb as a square root singularity. Right? But in general, it's something like this times some regular part. That depends on x. Okay? So this is true if I am far away from the poles. Right? I have many, many poles, and I'm far away. My x is somewhere in the complex plane. Then it's fine to replace sum by integral. But if you zoom, 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 zoom very close, then it's wrong. So it's like looking far away at a lattice of atoms, then it looks smooth. But of course, if I use a microscope, I see that there are atoms. Right? So here's the same thing. So we are just seeing it in the harmonic oscillator. We have many, many atoms. So if I zoom in close to x equal xj, I find a pole. But if I'm far away, I see the collective effect of all these xj's, and that's a cut. So that's really like a lattice of atoms versus a continuum limit, where I just see the global effect. Yeah.
The other sheet arises from the intuition of poles condensing into a cut.
Let me discuss it in a second, but the answer it doesn't. The answer is it doesn't, and I'll explain why in a second. Okay. The second sheet doesn't exist. It's an emergent phenomena, right? From far away. So you see, that's a very good question. But since some people are not familiar with these sheets, I don't want to emphasize too much that point. But in the original complex plane, you just have a function with poles. You just go wherever you want. And I mean, don't go really to the pole, but pass close to the pole, to the left. You can pass in the middle of poles, and nothing happens. Just a rational function or meromorphic function. You go around, and there are no things as monodromies. But then, in this classical limit, when you zoom from far away, a cut appears when you are from far away. Right? And now it looks as if now you can go through that cut and go to a second sheet that in fact doesn't exist. Okay? So it's kind of it's as if the bottom part, the second sheet, is kind of emergent. A black hole could be like that. Like from far away, it looks like it's smooth. If you would zoom in, it could be a bunch of poles. And then the interior will be an emergent thing, and it will not exist. So this was once Maldacena told me this. So that maybe a black hole could be a square root in disguise. Yeah. Okay. So what's happening is that the poles are condensing into a cut. Right? In fact, you can really take the distribution of zeros of their mid polynomial, and we could compute this function analytically and see that how it becomes exactly a square root. But the mechanism in general, it's this. We have many, many zeros indeed here, but we are from far away. All we see is a line that we cannot pass, which is the cut. Right? It condenses into a line. Okay, good. But what would we use this line for? We have this line between the turning points, right? But we know, on the other hand, what happens if I integrate, if I do a contour integral around all these zeros. So if I do a contour integral of my p of x dx around all these zeros, each zero has a residue h bar over I. Do you agree? Each 0 as a residue h bar over I. So let me divide by 2 pi. Now each 0 as, so now 2 pi I, and I need to divide by 1 over h bar. And now each residue, each pole gives 1, contributes 1, right? Because P is h bar over I cancel the h bar. The I joins with this 2 pi, gives 2 pi I, and the residue gives 2 pi I, so it gives 1. So this original integral is equal to n, which state I am. You agree? And I can be far away from the cut if I want, no problem. I don't need to compute this close to the zeros. This is a way of measuring which excited state I am. But on the other hand, when they condense into a cut, it means that this integral, when I go now around the cut, this integral of my P classical, right, which, okay, dx over 2 pi h bar, which, by the way, is just equal to twice the integral from a to b of P classical dx over 2 pi h bar. Because why? Because above the cut and below the cut, the difference is just a minus sign, right? You have square root and minus square root. So going above or below is the same thing. Should be equal to n. Huh? And this is WKB approximation, right? This is Bohr-Sommerfeld quantization. So it's not full quantization, but it's injecting the fact that your system is quantum mechanically, and that what you see as a cut is in fact a discretization of many quanta. Right? So for any potential, you compute the turning points, and the statement that the integral between the turning points of square root of the potential minus the energy should be an integer. That's a pretty good quantization, and that's semi-classical quantization. Right? So this is, it's not classics, it's already semi-classics, it's a bit better. And this would be semi-classical quantization.
Why do you get an n here?
Why do I get an n here? Yeah. Because this integral here is equal to this integral here, right? Or almost equal. In the classical limit, P is approximately equal to P classical. Right? So I'm computing the integral, and I can be far away from the poles. Far away from the poles, what I'm integrating, P is roughly like P classical, so I can replace P by P classical. And after I replace P by P classical, I can shrink the contour again. So this is just because P is approximately equal to P classical in the classical limit for energies very large. So for very large energies, this would be semi-classical quantization. Okay, so this was way longer than I thought it would be, but fine, I think it is fun, so that's okay. Sorry?
In the classical limit, the n also gets large?
In the classical limit, energies are large, which means n is large. So this is, n must be large, P is large, P is of order n, and everything is consistent, right? N needs to be large for sure, because otherwise it would not be a classical limit, right? So we need to be in the classical limit. We cannot be in the third excited state, right? The third excited state is very quantum, right? Classical limit is the 100th excited state or the 200th excited state, and n is how excited you are, right? So n needs to be large, right? Okay, cool. So this was just some fun with quantum mechanics, and with harmonic oscillators. And now I would like to start setting up what we want to do tomorrow, which is related to harmonic oscillators, but not to one, but to 900 harmonic oscillators. Okay. So we'd like to consider if this thing of the square roots, if it was not clear or something with this Riemann sheet, I hope it's clear that you don't need to think of the Riemann sheet. The Riemann sheet is something if you want to say, what happens if I go and do monodromies around the branch points? If I don't do monodromies around the branch points, forget Riemann sheet. It's just square root of x squared minus 1, and I don't start doing monodromies, then I can say that I'm in one copy of the complex plane. If you start doing monodromies, to properly explain that you need to go around more than once to come back to yourself, that it's better to draw a couple of floors. Okay? If it was a cubic root, you would draw 3 copies, because you would have to go once, twice around, 3 times around, and then you'll come back. So it's like a parking lot. Okay? But if you stay away from going around monodromies, and if you say, this cut I cannot go around, it's forbidden, then it's fine. Just keep 1 copy and just don't go around. Then you are good, right? If you are in the parking lot, you don't go up or down, you are good. Okay. Very good. So now what we are going to do, our goal will be to take a table which we think as a lattice right? And what we will do is we will punch this table and see how thermalization occurs. Okay? That's what I hope to start doing tomorrow. But before, what we want to do today is, as theorists, try to predict what we would like to measure and try to start saying what would we like to see. So here is the toy model I'm going to think for the table. I'm going to think that at each position of my table, I have some atom and its vertical position can change. So when I hit it, it starts moving up and down. Now it could also move right and left and so on, and I'm ignoring it. So I'm saying that at each point, there is a single variable, which is the height of where this particle is, and that's what I call x at position n, where n is a vector. Right? So n would be the coordinate of this point, and then x is where it is up and down. Okay? So this x, n, again, this is n m. It's a vector with 2, where this guy lives from 0 up to L, and so does this one. And this is our lattice. Y0, 1 up to L, 1 up to L. And this is our lattice. And I'm not yet specifying the model, but it will be a model, as any good plane, with translation invariance. Right? Things will be translational invariance. So it's always useful when you have translation invariance to decompose this mode into Fourier modes. Whatever Hamiltonian I will write, this is convenient because going to Fourier modes trivializes translations. So any interaction that will be translation invariant, it's good to go to Fourier. So I do 1 over the length of my system, summation over the Fourier modes, k, and then I get x with a hat of momentum k, e to the I k dot n. So here I'm just going to Fourier, okay, where, let's see, I'm going to momentum space, where we have periodicity, say. This is now something I'm imposing. So let's work with, let's say this side is equal to this side is equal to this. Right? And then periodicity means that this k that kx, for example, right? Kx and x, kx and ky, they live in a lattice of points minus L over 2 up to L over 2, an integer lattice like this. Let's suppose L is even, such that this makes sense. Because then, when n shifts by L, I get back the same thing. And reality, the fact that I want this x to be a real position, and here I'm dealing with phases. Why do I write phases and not cosines and sines? Because phases are mathematically easier to work with. But then I need to make sure that the positive k and negative k conspire to give a real result. So that means that my x hat k is equal to some real even function of k plus I times some odd function of k, where these two guys are real. And now I could, if I use this, I could just sum over k's which are positive, because then positive k's and right. So you see that k and minus k are even. The even part gives cosine. The odd part gives I times sine, and there is an I, so it gives sine, and everything is real, right? So with this, yeah.
Wait, one question though. You said kx and ky is between minus L over 2 and L over 2?
Yeah.
Is it possible this is and? Because k isn't k the momentum?
It's like pi over 2a or something.
Right. Because L has the...
Yeah. This is, sorry, what am I saying?
Or you can also say pi over 2L.
Sorry, you are absolutely right. So why did I write like this?
That would be pi over L, right?
No, of course. Sorry.
Is L the size of the table, or is it the number, like, is L an integer? Because you have n and m very important.
Sorry? L is an integer, yeah. L is an integer. Sorry, let me think a bit, because I think this is, I'm now confused by something. So I shift n. L. Yeah, that's definitely true, what you just said. So, yeah, of course, you're right. So, one second.
It's 2 pi over 2L.
2 pi over L. So,
Yeah.
So, yeah.
2 pi over 2L.
Sorry, one second. Minus pi over L.
No, that's actually correct. Yeah. Pi over 2L.
It's because you don't go to minus.
Because it's all...
No, I don't want to. Yeah, I don't want this. Sorry. No, this is, I'm just being silly. So, I don't want to say that this is because of periodicity. Sorry. No, this is silly. I just want to say that because I'm in a lattice, right?
Consequence of periodicity. You're quantizing your momentum because you have periodic boundary conditions, and what you wrote is correct.
So k should be 2 pi over L times an integer that goes from 0 to L minus 1. Or I can shift this zone, right? And it becomes, if I shift by pi over L, becomes pi over L times minus L pi over L, and I just shift this, and I get L, I shift by L over 2 minus L over 2 and L over 2. Yeah. Oof, okay. This is correct now, right? Or not? Maybe not? Yeah. Sorry, by this equal, I mean equivalent. Right? Momentum will be identified when I shift k by. I can shift everyone by an integer. Yeah.
Just a phase.
Yes. Right. So it's okay. It was okay. So periodicity means that e to the I kx and x would be e to the I kx and x plus I kxl. So this thing should be 2 pi times an integer. So kx is 2 pi divided by L times an integer, but this integer should run over L values, otherwise I'm repeating the same exponential. Which L values doesn't matter, I can shift. 0 to L minus 1 is easier to count, but minus L over 2 to L over 2, it's more symmetric. Okay? And it's when I consider this notation, then I have this nice even and odd reality conditions. Okay? So good. And this change of variable is good whenever we have translation invariance. So here, sorry, I have kx is given by this. So kx and ky, they both belong to this set. Okay. And now notice that this is a nice normalization. It's nicely normalized. So there is a nice normalization. Since when we sum over xn square, which is like computing the norm, if I think of my xn as being a vector, sum over xn square is like the norm of my vector of x's. And this will be a nice normalization because this will be equal to the sum over k of xk square. And let's check that this works. But that's what I mean by a nice normalization, that summing over n's or summing over k's, it's the same, which means that this is like a nice rotation that just rotates from position space to momentum space. And why does it work? Let's see that we have this sum. Each x has 1 over L, so there is 1 over L square. And then I have now x squared, so I sum over n, and then I sum over k, and then I sum over k prime. And then I have x hat k prime e to the I kn plus I k prime n. Right? But you see that this sum over n, the sum over n just cares about this exponential. Right? And what is this sum over n? So when k is minus k prime, I'm summing 1. Right? K is minus k prime, I'm summing 1. And how many terms I have? I have L squared. So this n will give me L squared delta when k is minus k prime. And in fact, if k is not equal to k prime, then this sum is just 0. Right? So if k is not equal to k prime, I'm just doing a sum that, that gives me 0. So this is the exact result of what the sum over n gives me. Is it okay? I'm just using the sum over n of that exponential is this, what I just wrote now. Right? You can just do the sum explicitly. It's a geometric sum, and you get, and you see that right away that you get 0. Right? And therefore, what do we get? We get, therefore, that this becomes sum over k only, because the fact that k prime is minus k gets rid then of this sum. So suddenly we did the sum over n, we did the sum over k prime, and we got just the sum over k of x hat k, x hat minus k. But x hat minus k, if you see, you flip k to minus k, you flip the odd part, which means you put a minus here. So that's the same as complex conjugating. So that indeed gives what I said we should give. Right? X minus k is just the conjugate of xk. Okay, good. And now, let's start checking why this going to this mode is nice. Because now we could imagine in our lattice, we have our table. And the most natural term that we would really like is that when we have our lattice, we put some kind of spring between neighboring atoms. And what do I mean by this? I mean some interaction that would be x n minus x n plus L, where L are the neighbors. And I would sum with square with some constant kappa, and I would sum over all sides and over L, and L would be, say, up, down, left, right. Right? So N would be this neighbor, this neighbor, this neighbor, and this neighbor. Right? So L is 0, 1, 0, minus 1, 1, 0, minus 1, 0. Right? And what does this become? Let's do this very simple exercise. The square I write one term times the other, so it becomes sum. It becomes equal kappa outside over L square. Each x is 1 over L. And then I have a sum over n over k prime over L. And then what do I get? I get this, where I use the definition. So I get xk times the exponential minus the exponential which shifted L, which shifted n. So it becomes k. Let me write, and then it's going to be obvious. X cat k prime e to the I k n plus I k prime n. This term is common to both. But now let's fix what is missing, which is this term minus this term with L. So that gives 1 minus e to the I k L. And from the other, 1 minus e to the I k prime L, where all these k's are vectors, right? So let's put vector everywhere. Vector, 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 vector. Okay? Is this clear? Yeah? So I just wrote x minus x times x minus x, and each x minus x is, I use the definition. Right? Because it was quadratic, I have k and k prime. It's exactly the same that I used here. Right? But I just wrote x minus x using that definition is this term with times 1 minus e to the I k L. Right? Now, same story. L, the sum over n, now just appears that. So that sum over n sets k prime to be minus k and kills the L square, because it gives L square times delta function. So that sum over n does that. So it kills both this summation, right? It kills both the summation over k prime and also the L square outside. Then when k prime is minus k, this thing here becomes, when k prime is minus k, you see that this term is just a complex conjugate of this. So, and indeed, if you factor out e to the I k over 2, this is a sign, and this is also a sign, and they are the complex conjugate of each other, so it's real. And this is a sign I need to divide and multiply by 2. So this becomes 4 sine square of k L over 2. Okay. And this term, I sum over up, down, left, right. Up and down give the same thing because this is even. If L is positive or negative, it gives the same thing. So this term will give 8 sine square of kx over 2 plus 8 sine square of ky over 2 after we do the sum over L. So all in all, this term here, so we already did one computation here. That was a nice transformation. And now we just figured out another one, which was that this interaction in our lattice is equal to just sum over the modes 8 kappa sine square of kx over 2 plus sine square of ky over 2, everything times xk square. And therefore, our Hamiltonian for our table that we are going to try to thermalize, I want to write it like this. I want to say that it would be a sum over all sides of the table. And then there could be some momentum of my excitation over 2m. It could be oscillating, right? There is some momentum. By itself, it could be, there could be some restoring potential that for each n would want to make the particle oscillate. So this would be like saying that it's a bunch of independent harmonic oscillators. And then there could be some kappa sum over the neighbors L x n minus xl square. And this is a bunch, it's coupled, sorry, n plus L, right? So these guys are coupled. And going to Fourier was very nice because it totally decoupled all the modes. And therefore in Fourier it's much nicer, it's just sum over the Fourier modes of the sum over Pn square, because it's a nice rotation. It is just sum over pk square in Fourier plus m omega k square over 2 absolute value of xk square. So for each mode, I have an harmonic oscillator where this omega k square is what? It's omega square. I just read off from what we computed. This omega k square is omega square plus 8 kappa over m. Let me try not to do a mistake. Times sine square of kx over 2 plus sine square of ky over 2. Right? Therefore, right, this is my Hamiltonian, and it's just a bunch. So this is just, right? So there are just L square harmonic oscillators. Should it be 16 here? I don't think so, but let's see. Maybe yes. Yeah. So the way I will, yeah, it should be. So let's divide by. Great. And now it's L square harmonic oscillators, but what's important actually is what I did not write, which is they are decoupled. And because they are decoupled, our partition function, right? Our partition function is just the product over each of these oscillators times the partition function of each individual oscillator, which is what? This one is just what you computed in class, right? So this is just what you computed yesterday for an oscillator. You just sum over n from 0 to infinity e to the minus beta omega k n. Right? Well, in fact, if it's harmonic oscillator, there is a 1/2 as well. But this 1/2 is irrelevant, as we will see, because we want to study a classical table. So with classical table, we don't care about constant. Right? And this becomes equal to the product over k, right? E to the minus beta omega k over 2. That's from the 1/2. And then from the geometric sum, 1 minus e to the minus beta omega k. And that's approximately equal, right, at large energies, or if you want, at large beta, at small beta, at large temperatures, which is the classical limit. So at small beta, when temperature is large, such that we can ignore quantum effects, this exponential is 1. Here I can expand, and I get product over k, 1 over beta omega k. And therefore, z, my partition function, z would be equal. Now it's a good time to take the log of z, or say z is exponential of the summation over k, right, of log of this quantity. That would be log of omega k. So the log of omega k, omega is a square root, so there is a 1/2, and then log of omega square plus 8 kappa over m sine square of kx over 2 plus sine square of ky over 2. Right? And then, very important, there was a beta, and there are L square modes. So there is minus L square logarithm of beta here. And therefore, we see that when the table will thermalize, when we reach thermal equilibrium, what's the energy, the relation between the energy and the temperature? Well, let's work it out. Remember, the energy is minus derivative with respect to beta of log z. And therefore, we get that the energy is, the minus cancels, and I get log square over beta. So beta is equal to 1 divided by the energy per site, which is the kind of thing that we have seen already. So we know what beta will be. Beta will be the energy that we give the system, just the inverse 1 over the energy per side. And once you know what beta is, we know what the partition function should be, and we could try to compare this with thermalization. Okay. Let me just okay. So now I will say a few more comments about this solution next time, but just in 1 minute, let me just say then what's our goal. So our goal, as we said, is to start with a table, and then we punch the table. Right? So we punch the table, there is some boom. Right? So we punch the table. So we start with some E, which is E initial. Okay. And we start with this table. And of course, this full table is not the micro-canonical ensemble, right? Micro-canonical. I'm not summing over states. I just punch it once and that's it, right? So I punch it once and let it evolve. I'm not summing over all possible states. And it's definitely or the canonical ensemble. But we know that it should thermalize, so it should work. Punching a table, we do know it warms up. So effectively, it should behave as a thermal state. Okay? So the idea is we start with this energy, we thermalize, we wait. Right? Then, so we start in the beginning where here it's hot and here it's cold. And then we thermalize. So after it thermalizes, now it's homogeneous. When it's homogeneous, we know that it's at some effective temperature beta given by that, which is just 1 over the energy per site. And then we could, with this beta, for example, compute expectation values of, say, the propagator, which are the correlations between two x's at some effective temperature using that partition function z that we computed there. Or we could consider a table and consider looking at subsectors and asking whether here we get the density of states that we would predict. Density of states at some temperature bit that we would expect for after it thermalizes. And those are the kind of things that we are going to do. But we should have in mind that there is a challenge here. And the challenge, one challenge that we have, is that we want a table and we don't want a drum. Namely, I don't want to punch a drum. If I punch a drum, I make music. I don't thermalize. Okay? So I make a drum and I create some wave that moves boom, 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 boom. Okay? So what happens is that what I would like to avoid, right? A drum where I hit and I produce music, right? Which means that what I don't want is to punch the table and to get some wave that just propagates freely and goes back and forth. Instead of thermalizing, I don't want to create some wave that just moves, comes back, moves, comes back. If I do it, what do I expect to see? For example, when I study what's the average energy on a bin, I see nothing and then a burst of energy passes. then nothing, and then a burst of energy passes. Which would be what would happen if I punch and I let some energy waves just move. Pong, 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 pong. Instead of thermalizing, I put some observer there, and I just see waves of music passing left, right, left, right. But that's a bit of a problem because we are solving a free theory. This theory is effectively free. It's just a bunch of oscillators. Right? So if I just start with this model and I punch the table, you can just take the original configuration, decompose it into modes, and that's the final configuration. You just evolve each mode individually. So what you will see is that if we just punch the table, namely, if we take this model and classically evolve its equations of motion, where starting with some random velocities in a corner, it doesn't look like it thermalizes. So if we just evolve this model, the challenge will be that we start with, say, the energy in some bottom corner where it starts cold. And here it's a top corner. So this is the energy in a top corner, top energy. And here it would be bottom energy. And we would expect that if I consider two corners, one where I punch it and one where I don't, that the one where I punch starts very hot and then equilibrates. And the one at the bottom starts very cold and then equilibrates. And if they have the same size, they should give the same thing. But what could happen if things don't thermalize so well is that these fluctuations are not of the order of square root of the system, but are much bigger. And what could happen is that you have some big fluctuations, and here some big fluctuations, indicating that it's more like some waves that are passing boom, 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 and you don't see it going into smaller modes, right? In other words, there is no transfer of energy from modes. Whatever distribution of modes you start with, they are not going to go into Gibbs distribution because it's just a bunch of free oscillators, right? So each oscillator, I start with some oscillator, and it doesn't go to Boltzmann distribution. It doesn't converge to this distribution here because it just doesn't move. They are free. Whatever I start, this is what that's what it is. So it cannot evolve to another distribution. Okay? So that's a challenge, right? So what could we do? Proposal for this challenge. What would you suggest? Because I'm actually not 100% sure. We'll have to solve. We know some things that work, but maybe there are other nice ideas.
Add other terms, like.
Very good. Very good. Excellent proposal. Why don't we add some extra terms? For example, we could, now you don't need to write this down because I'm going to repeat it tomorrow, but we could imagine adding some terms, say some mu, and then some, let's not break parity, so let's say some quartic term, for example. Now, it's no longer just a bunch of free oscillators. Now there is a nonlinear term. And this nonlinear term, because of this nonlinearity, it allows modes of different momenta to couple to each other. Now, this allows leakage. It's like now the initial distribution of modes is not the final distribution of modes. They will now dynamically distribute themselves. Okay? So that's a good idea. Now, it has a small drawback, which is that as humans, we don't know how to solve this x to the 4, right? We know Gaussian integrals. If we have x to the 4, now I don't know how to solve. So it's good that it thermalizes, but now I don't know how to write z that we can compare, right? So that's kind of the challenge that we'll have to think a little bit how to do. But we can also think that a bit physically what this could be doing. Imagine you want to thermalize a drum, right? So you punch a drum and it gives music instead of thermal, right? So what could you do to thermalize the drum? I think what you could do is the following. You could ask a friend to hold the drum very, very tightly and to push it, right? And that will enhance nonlinearities. And now you punch it and it doesn't do music properly because it's very tense. It's not that it's relaxed frequency. So you ask people to push the drum from the sides and you hit it. And now the drum makes some stupid music because it's not, it's like huge tension. And that huge tension, microscopically, it's enhancing these nonlinear terms. And now it thermalizes. And then what do you ask the friend to do? To just release it, right? Let it go. And then after you let it go, it now will be thermal and it will be the thermal drum. Okay? So that's what we are going to do. We are going to add this term, But we are going to add it for some time and then turn it off. And that's like holding the drum and then letting go. And then we have solved both problems. It will thermalize, and at the end we'll be able to compute and therefore to compare the result of thermalization. Okay? So that's our goal for tomorrow. Okay? So that's what we do tomorrow.